A very good morning to all of you. My name is Sabir Khan, and today we will discuss about the strength of material. And today's topic is SFD and BMD on simply supported beam due to UDL load. So let's start. In our last lecture, we discussed about simply supported beam, but the SFD and BMD due to point load. So in this lecture, first of all, you have to calculate the RA and RB. So in this problem, the load is symmetrical. So reaction at A is equal to reaction at B. But in general, that is maybe we have unsymmetrical loading. So we have to know about the how to calculate the reaction in case of different kind of load. So if we have unsymmetrical loading, then we have to take movement about A or B. So let's check movement about support A. Okay, so that is RB into L, RB into L, that is in anti-clockwise direction, and then minus W into L, minus W into L, W into L, that is load, total load, and that will act on centroid of the load. So that is L by 2 from the support A. So WL load, and for movement we have to multiply it with the distance from A support. So that is L by 2. Okay. So that is equal to 0 because support A is simply support. That is equal to 0. Okay. So if it is equal to 0, then RB is equal to W L by 2. Okay. So if the load is unsymmetrical, then we have to take the movement about its take the movement about support A or support B. Okay, and calculate the values of reaction. So RA and RB is equal to WL by. Now shear force at a distance x from B support. So shear force at distance x from B support, that is one due to the reaction and second one is due to the UDL. So due to the reaction, that is upward and that is on right side of the section, so that is positive. WL by 2, that is our reaction, minus W into X, that is our load. Okay, so shear force at B where X is 0, so you have to calculate shear force at B where X is 0. So we have to put the values of X 0 in the above equation, and if you put the values of X is 0, then shear force at B is no doubt that is WL by 2, that is equal to the reaction at B. So and shear force at mid span, so we have to put the values of X for mid span, that is L by 2, and if I put value L by 2, then the values at mid span is 0. Okay, third, we have to take the value of shear force at X equals to L. So in next we have to put the values of X is equals to L. So when I put the value X is equals to L, so that is plus WL by 2 minus WL, that is minus WL by 2. So at B, that is positive WL by 2, at midpoint that is 0, and uh, at end the values are minus WL by 2. Okay, so basically the this is our shear force diagram, and one second, that is the calculation for WA. And clear, all right. Okay, so if I'm talking about bending moment at section, so bending moment at any section, that is equal to reaction at B multiplied by x minus Wx square by 2, because Wx is the total load, and Wx square by, okay, 2. So okay, that is the movement equation at x distance from the B support. Bending moment at B, where x is equal to 0. So bending moment at B is 0. We know that is 0 because the support is simply supported. So it's okay. Anna. Then bending moment B is 0. Okay. Bending moment at A, x equals to L. If I put x equals to L, then that is WL square by 2 minus WL square by 2. That is also 0. And we know that point A is support A. So support A is a simply support. So on simply support, the bending moment is 0. Okay. And for maximum bending moment, we have to use the maximum minima condition. That is, we have to differentiate movement with respect to x with respect to distance, and find out the values of x where the this condition satisfied, that dmx over dx is equals to 0. Okay, so dmx over dx, that is plus wl by 2 minus wx, and from this equation we got the values of x, that is l by 2, and we put the values of x l by 2 in our movement equation. Okay, so we put the values of x in our movement equation, that is wl by 2 into x, that is l by 2 minus wl by 2 into l by 2 whole square. So that becomes the maximum movement on the beam is wl square by 8 at its center. So that is the maximum. Now this is we have to discuss relationship between load, shear force, and bending moment. So if I'm talking about relationship between load, shear force, and bending moment, then then there is a beam in which some kind of load gradually, it's not gradually increasing, but increasing at any point. Okay, so it is not uniformly varying. It is varying load. So if I'm taking 2 points A and B, which are the closest one. So if I'm talking about 2 points A and B, then if shear force at A is F, let's assume, and bending moment at A is M, then the shear force at B will be something, yeah, something increasing or decreasing. Okay, so F plus delta F may be negative, may be positive. It depends on the type of loading. Okay, so in similar way, M plus delta M. So delta M at B point movement, then delta M is also positive or negative. It is also depending on the type of loading. Okay, in the direction of loading. So and the UDL, that AB distance is delta x. Okay, So distance between AB is delta x, and the load on this is W unit per length. W per unit length. Okay. So it is not a UDL, but for a small part of beam, we can assume that this load is around UDL. Okay. So that is our load. Then we have to calculate the relationship. So I can say that F plus delta F, F plus delta F, this total load, summation of load in y direction, that must be zero, but total upward load is equal to total downward load. Okay. So F plus delta F is equal to F plus W delta X. Okay. So F plus delta X, that is upward load, and F, that is downward, and W delta X, that is also downward. So these loads are equal. So from here, we can say that delta F is equal to W delta X, and W is equal to delta F over del X. For the del X is assumed to be 0, then I can say that W is equal to dF by dx, or I can say the partial differentiation of force of shear force is equal to the load per unit length. Okay, that is the relationship between shear force and load. Now, what is the real relationship between movement and shear force? Then we have to take the summation of the total movement clockwise equal to anti-clockwise. So if m plus delta m plus wx, okay, m plus delta m plus wx, okay, m plus delta m plus w into x, w into dx, sorry, so w into delta x into delta x by 2, that is the movement due to the UDM, minus m minus f plus delta f dx, that is the uh, movement due to the shear force, that is equal to 0. So from this above equation, we can calculate the, we can calculate the values of delta m, that is f plus delta f dx, and we have to neglect the values of d delta x square, because delta x is a small quantity and delta x square is much lesser quantity. So we have to take the delta x square is equal to 0. So in this above equation, if I put the values of delta x square is 0, or delta f delta x, that is small force and small distance, that is also a small thing. So we can neglect that, because the differentiation of partial thing will be neglected. Okay, so f is equal to delta m over delta x, delta m over delta x. So that is the relationship between f and movement and shear force. That movement is equal to integration of f dx, or shear force equals to differentiation of movement about x. That is the relationship between movement and shear force. Okay, so we can calculate this relationship. Thank you very much.